I didn't cause anyone to come for no reason on Monday. Hopefully you got the announcement. Allergies just hit me really hard. But we're okay on timing. So we're here today. We're going to do our 9.5 and P2. So those are incorporated together. Wait, isn't this? Okay, here we go. So we're going to do that today. We'll be fine. And it kind of leads into the P.3. So we're into the appendix stuff, and we will have all next week as review. Uh, Probably the most important day will be here. I'm assuming I will have the final exam to view by this Friday, so I can do doubly focus on exactly what you need to do. But we'll go throughout the week. Uh, so far, the study guides have been fairly accurate. When I get it, sometimes I've made a few adjustments because there's some types of questions that were a little different. So we'll make sure that that's all that when you show up for the final, it's not a surprise. It'll be everything. We'll get it all covered next week. Uh, so a little bit of mix of answering some questions, maybe doing some work. We'll record whatever we do as a class. I will work this weekend, since Friday we will have all our content covered, to start making some videos, because I think that's also a good way to review. Is you're at the point where you've got it all. We just need to review and maybe ask some questions. So I want to give you the room for that. So we'll just keep moving forward. Any questions or comments or requests? Okay. So we're going to leave that part. The other, here we are. So a couple things I've updated. First of all, there is this chapter P. I finally found where it was. I was looking for that all over the place. It was in WebAssign. I was poking around. I can't remember exactly how I found it, but there's something like it's like resources, and there's a couple PDFs in there. I've posted it here so you don't have to go searching for it in WebAssign. I'm sure you have access to it as well. Did anyone find that before? I don't know, it took me all semester to find it. Anyway, so I did. So anyway, it's right here. It's a PDF. It has P1, 2, and 3. What I've done is for P3, there was no other content, so I have actually copied and pasted screenshots into the PowerPoint that we'll use on Friday. So, and there's parts of it we're not doing. So, but it's all there. Once you see the parts we do, if you want some more explanation, you could go in and read the chapters and see their examples. But that's what we'll be working on today and Friday. So we're going to go into probability distributions. The other part, the way I'm going to show you how to do things is going to be heavily dependent on using technology, using a graphing calculator, either TI-84, or I've also got the Casio. So because I've done it the other way. I'll show you both ways. You can look it up in a chart. That's actually a little bit more archaic, a little bit more difficult. But then I'm going to focus on using the graphing calculator. So I've got mine ready to go here. But there are these videos. There's the Casio video. What I found, I have a Casio, and the part that you need to use, mine was like 2 years old, and last year they did an update. So the video assumes you have the update. So there's a little video to update your Casio if you've got one of those. I'd be happy to help you with those kind of things as well, either during office hours or next week. And then if you've got the TI-84, this is a video that will show you everything we're doing. And again, it's somebody else's video. I watched it to learn how to do it. I'm going to show you how to do it, but those are there in case you need them to go back. It's how I learned how to do it. So there's a full PowerPoint. Again, I've cut some of the things out, so we'll just go with this one. It's a little bit of a shortened version. We'll focus on the examples and on using the technology. And then remember, there's the review a little bit further down that will be helpful to maybe start going through as early as this weekend or earlier if you haven't already. So let's see, let's just go into this. Okay, so the normal distribution. And actually, we're covering more than just the normal distribution, but so that's where the P2 comes in. We're going to look at various distributions, okay? But the normal distribution we think of as the bell-shaped curve, and it is very helpful for a number of different types of distributions that we look at. In fact, the word distribution itself may not have a lot of meaning, but what we mean is that it's a collection of all the different things that can happen, right? Different probabilities. Like the distribution for rolling a dice, you get either a 1, 2, 3, 4, 5, or 6. Each has their probabilities. So we do the same thing with all of these. So we're going to start with what we've been working with primarily so far is discrete random variables. So this is like, it can be either 0, 1, 2, 3, 4, 5, all the way to 10, because this is coming from a Bernoulli trial, either with 10 or 15 independent trials. So out of 10 trials, how many times was there a success? Whatever it was, it could be flipping a coin, but this would be sort of the look. And we see it has sort of that bell-shaped curve, but this was a discrete. It was either 3 or 4, right? It wasn't, you can't get 3.5 heads. You either get 3 heads or you get 4 heads. So that's what we've primarily been working with. We're going to transition into continuous variables, and we'll see how that works. But it comes from these concepts are very similar. Okay, so we could calculate with these, say, I think it might be on the next slide, but if you wanted to calculate the probability of getting a 7, right, we could say, okay, here's the 7. We could be, you're going to get a 7, and then we come over here, and that looks like about 0.13 or 0.12. Again, we're kind of estimating. So about a 12% chance of getting a 7. So that's how we do it. We could also, I'll come over to here with the 15 trials. Again, the more trials, the more it looks like a random variable. We could also get the probability of being from 5 to 9, say. And what we would do is we would, let's see, which one's 5? This is 5 all the way to 9. And we would add all those probabilities for each one up. We could do it that way too. But basically what we want to see is we're getting the area under that sort of bell-shaped curve. And that's where we're going to go with the continuous random variables. So, and this kind of gets in, we could go x equals 3, which would be just here, right? So that's about, also maybe about 0.12. Or we could get from 3 to 5, which is the darker green ones. We would add those together and such. And notice one of the defining characteristics of a probability distribution is that if you add them all together, they've got to be equal to 1 or 100%. Okay, so again, usually we're getting the area as a decimal, but we could easily convert it to percent. So 0.5 is 50%. So far, we're doing okay? Okay, let's jump in. Oh, one more thing. Let's see. So yeah, we could do the area. Basically, we're looking for the area between 2 points. We'll call them A and B. Okay, so those are 2 measurements. What percent of the distribution or probabilities are between those two? We'll be doing that a lot. And with the histogram, it's easy because, basically it's either 3 or 4, so everything is included in those bars, and we do that. But as we get to continuous random variables, we could get where it's 3.5 or 3.57 or so we could get any value in between there. And so what ends up happening is it's a nice smooth curve. The area is still 100%, right? Is under the curve. And what we're going to be doing today is finding what's the probability that a measurement is somewhere between A or B. Okay, so these could be test scores. What's the probability of scoring between a 70 and an 85%? We might be doing that. Remember, what's in the middle? What did we call the middle of this distribution? The word that starts with M? The mean? It's the mean. It actually, on a standard normal, it's also the median, and it's also the mode. But so you would have got it right no matter which one of the M words you chose. But we'll focus on, we call it the mean. And remember, from the empirical rule, we'll see how that comes about, that we had standard deviations, so percent below, percent above. And if we were one standard deviation below to one standard deviation above, the empirical rule said 68%. And we're going to see where that comes from. Two standard deviations, two below, two above, was 95. So we'll see, we'll actually do those today. And so basically we can get the probability between two numbers. Now, the one thing we can't do with continuous, you can't get the probability of being exactly equal to 1 or a number, right? Like, what's the probability of being equal to that? Well, that has no area. It's just a line, right? Whereas in discrete, it was a whole bar. So we could actually get that area. But in this one, you can't get the probability of being exactly at an area, but you can get the probability of being between A and B, 1 and 2, 1 and 3.6, something, So that's what we're going to be doing. And we're going to use technology to come up with it. And I'm going to give you two options you can use. One is graphical, and you will actually see it. You'll see the picture, you'll get your answer. The other is just more, you plug in the numbers and you get your answer, which you might want to use both, maybe the picture at the beginning, but we'll go through that. So this is the stuff from the appendix. So we're also going to talk a little bit about just distributions in general. We're not going to get deeply into any of them, but we will, in the homework, there are a couple different distributions that are not the normal curve. So we're going to take a quick look at those. I think there's 3 of them. We'll see. And then we'll get deeply into the standard normal distribution. Okay, that's what we're going to focus on, because that's, in statistics, that's typically what you'll see. But there's also these other distributions that may not be the bell shape. They might be skewed one way or the other. So we're just throwing this in there, that there are things that exist that way. But for any probability distribution, these two things have to happen. First of all, every probability, right, has to be greater than 0. You can't have a negative probability. So, and we're going to do this as functions because these are continuous, right? So every y value for the function that we're considering has to be above the x-axis, has to be positive. Okay, so if it goes below, then it's not a probability distribution. So that's going to be one of the answers. So homework, you'll do about 3 or 4 of these where you just identify, is it a probability distribution or not? If it is, you just say, yep. If it isn't, you got to tell it why it's not. So one reason is we have some negative y values in that region that they're giving us. Okay. The other thing that happens, and again, it might not be everywhere, but they'll give us some boundaries from A to B, whatever that is. It could be from 0 to 1, whatever, A to B, that all the distribution, the area has to add to 1. So we'll see how we can do that one. If it's greater than 1, it's not probability distribution. If it's less than 1, it's not probability. It has to be exactly 1. Okay. So those are and if it fits those two things, then yes, it's a probability distribution. So let's look at a couple of examples. So this is from the back of the section in the appendix. We'll do number 8. So the way we can do this, the question is e to the x a probability distribution? And what you see is what we're going to use is integration. So we're bringing in our calculus. But the cool thing about this is we don't actually have to do the calculus like we did earlier on. Okay, we're going to use technology. We're going to graph this, and we're going to have it give us that interval for us. Okay, so how do we do this? Let's Bless you. Switch over to the calculator. Won't do both at the same time. You'll see this will come back up later. I'm going to leave it there because I didn't want to retype it, but you might want to keep that stored in your graphing calculator for future. And you'll see, we'll use it a little bit later. But our function was e to the x. And to do the e, you have to go second natural log. There's your e to the x. And we want to see if this is a probability distribution. And they had us going from 0. Let's see if I can get back to it. To ln of 2. Okay, so let me see if I do this. Then I can go back and forth a little easier. So what I have to do is I have to graph this, and again, sometimes it's you'll see what I've done with my window is I have the y going from 0 to 0.5. I think we're okay leaving it at that, maybe 0 to 1. And I have x going from basically negative 4 to 4. I think it'll fit, so that's not a big deal. Let's see if it fits. We want to go from 0 to natural log of 2. Actually, let me just do this. Let me do a zoom standard, and I'll talk about the window later. So yeah, we see it. So we're going from 0 to wherever natural log of 2 is. The way we get the area under a curve is we have this tool here, second calc, and this integration tool. Again, if you've got a Casio, I'll work with you on some of those techniques. I think some of these are in the video, some might not be, but we'll figure it out how that works. But that's the key part. So we're going to go from 0. That asks for a lower bound. The upper bound, this is kind of weird, but you just have to put in, not shift, you put in natural log of 2. That's a number. It'll calculate it for us. And then it shows us what it's shading, and it gives us that area is equal to 1. So did it fit the 2? Yes, it is all positive. All the y values are above, the graph is above the x-axis for that portion. And between 0 and natural log of 2, it has an area of 1, 100%. So we just come back and say, and I'm going to go back and forth, so it's a little funky, but yes, that's all we have to do is answer it fit these 2 items. We checked them off. Okay, but that's how you're going to test it. You're just going to graph it, find the area under the curve. Let's do the second one. X e to the minus x squared from negative infinity to positive infinity. Well, how do I put negative infinity into my calculator? You don't, but this is how we'll do this one. So again, we come back, we're going to graph the new one. Was x e to the minus x squared, I think it was. And you'll see that's similar to what's going on here with the standard normal, but it's not the same. And you'll see, I don't think this one works, but let's go to the graph. Oh yeah, do you see what's happening here? Let's zoom in a little bit, but it's below the curve, isn't it? It's below the x-axis. It's got y values that are negative. Does that violate? Yeah, it doesn't fit the first one, right? The first one has been violated. So we don't have to go any further. We don't even have to, because it's going from negative infinity to positive infinity, but somewhere in there, this whole side is actually below the x-axis. So that didn't work. You'll see the next one takes care of that part of it. So we would say, and we're supposed to give the reason, so here it would be no, there's places where f of x is less than 0. Because something like that. Again, on the homework, it gives you multiple choice, but look for that choice that basically says there's negative y values. F of x is below 0 at some point. Now, there's points where it's above, but okay. So the second one is basically the same thing, except it's got an absolute value around the x, so that makes negatives positive. This one might work. So we just come back here and we go and change our function. I'm going to insert, and there's if you go to the math key and then over to number, there's ABS, which will put in an absolute value. Okay, so math, number, ABS. And there it is. I'll put in an X here, and then I'll delete this X. So now we've got the absolute value of X. And we're going to see it's a very similar graph, except now everything is above the x-axis. I'm going to go in a little bit closer since it's so small. I'm going to make my y maximum. I think I can just make it 1, and we will see it a lot better. And actually, I don't need to go too far. I'll go from -1 to 1. There we go. We'll go to the graph, and that's what it looks like. Kind of funky, but now what do we need to do? We need to see if it goes from negative infinity to positive infinity. Is this 1, right? Because it's the first, it's positive. So option 1 is checked off, but is the area under this curve 1? Well, what I do is we use our idea of limits, right? I can't put in infinity. And on top of that, when I graph something, it won't give me an answer if I go beyond my windows. So my windows are currently going from -10 to 10, so that's all I can see. So I'm going to give that one a try. I'm going to go second calc, and I'm going to go from -10 as my lower bound to +10 as my upper bound. And it tells us that that area is 1 between those two areas. And what I see is that that graph goes down almost, it's like asymptotic to the x-axis. It's getting very, very close to 0. I feel fairly confident that it's, if I go out further, it's still going to be 1. But maybe I'm not confident. So what I'm going to do is I'm going to get my boundaries to 100, -100 to 100. And if it's still 1, I'm going to say, yeah, it worked. Okay. So this is, and after a while, you'll just see, as long as you can kind of, as long as it's going down, this, we got enough. If it wasn't, if it was like 0.98 something, I would go out further and say, because I can't, we're supposed to go all the way to infinity. So what I did is I just played with this a little bit, but I can convince myself fairly readily. And there was a few that I did that you actually have to go this far to get it to be equal to 1. But I just put my x's out further. I go to the graph. You don't see as much detail because we're way out here, but we can go second calc. And again, put the lower boundary. Now I'm going to do -100, and I'm going to go the upper limit to +100. And again, you might, what? It says that that's equal to 0. I didn't do that. Well, I'm going to go back with the other one. That's weird because if it had area of 1 going from -10 to 10, it's still got to have 1 there, right? Unless it subtracted it off or something. That's weird. I think it's a calculation error or something. I have no idea because I can see there's some area in there, but it's saying some is getting subtracted off or something. But it just shows you the problems we get when we try to go out to infinity. Okay, but just go out a little bit. As long as it's asymptotic to the x-axis, we should be fine. Maybe, let me try this again. Yeah, I don't want to spend too much time on this, but let's just do this going out to 50. So we'll go from -50 to +50. See what it does. That's -4. It's still telling us 0 if we go out much further. Unless it's under the curve somehow, but The other ones all worked. It gave us 1 as far as I went out. So I would say the only thing I want to look at, let's go to the table. Let's see if it ever becomes table set. Let's go to auto. I want to start way out there. Let's go out to 50. The only way we could go from having an area of 1 to having an area of 0 is if it went below the x-axis. Let's change by ones. Go to table. Oh, these are all zeros. Yeah, it doesn't go below the x-axis. So that's one of the things I wanted to check, is that they're very close to the x-axis, but they're asymptotic. So you can't go from having an area of 1 to having an area of 0 unless you subtract it off some, right? I'm going to stick with this has an area of 1. Okay, so it's just our calculators are not perfect. They're running some kind of a calculation in the background. These are just showing small numbers. When you get e to the -7, that's 10 to the -7th power, so they're getting closer and closer to 0. Yeah. And then going the other way. So when we went from -10 to 10, we got our area of 1. So I'm just going to say, yes, got to move on because we've got more to do. So I'm going to say yes on this one. And again, once we say yes, we don't have to say anything more. It just is, because it fit both of them with those. But do that kind of analysis. That's how we get through this part. Okay. Again, there's only like 3 questions. They're all multiple choice. So let's do that one. So then there's different types. And again, there's like a question on each of these. So we don't go too deeply into these, but there are one of each. So uniform density. Uniform densities, everything has the same probability. This is like rolling a dice, right? Probability getting a 1, 2, 3, 4. All of them have a same probability of 1/6. So there's a number of things out there where everything's sort of equally likely. That's what's called a uniform density. And to get the function that we use is we simply take the 2 endpoints, whatever they give us as a and b, and it's 1 over b minus a. So we're whatever that interval is. And doesn't that kind of make sense? What that's saying is that going from a to b, if the function is 1 over b minus a, it's going to be level here. This will be an area of what? Well, the base here, what's the length of the base? That is b minus a. It's the distance between b and a. And if we multiply this times 1 over b minus a, what do we get? This cancels with that. That becomes 1. It's 1. It's an area of 1. This is a probability distribution, as long as it fits that, right? So if there's a question about uniform density, you're going to remember that this is the formula. Maybe the picture will help us remember better. So let's look at an example. Going from C to D. Again, we might need to to find the area, say, so uniform density is going to be the function 1 over b minus a. So if we want to find the probability of being between 2 points like B or C and D, so this is within the full distribution, right? This is the whole distribution. We just want to find a probability being between these 2 points. And there's a question in the homework like this. All we have to do is we take our function going from C to D. Okay, so let's say that those numbers, the random, so x is a random real number between 0 and 5. What would be the probability in this case if it's uniform, random real number between 0 and 5? I think the question said uniform, going from 2 to 4.5. Okay, so the way to work this, right, the function for this uniform density is simply going to be 1 over 5 minus 0, which simplifies down to 1/5. And what we need to multiply by is the area or the length of the base, right? And the base is goes from 4.5 to 2. I guess maybe, yeah. And then, so that's in the numerator. That's taking the place up here, so because we don't want the whole area. And then we're over 5, which came from this, right? This calculation here. 4.5 minus 2 is 2.5. Divided by 5, which gives us let's use this one because it's a little easier. 2.5 divided by 5 is 0.5, or 1/2. Okay. So for those ones, for uniform density, we don't have to go to the integral. We could, I guess, you could graph that integral of 1/5 and then go and do it, but we don't need to. Okay with that? Okay, so just think of uniform is always going to be a rectangle anyway. Okay, exponential density function. Again, there's this one. There's at least one question. There's one question in the homework that deals with this, so I'm going to do it a little quicker. I'm not going to go through the full example. If you want to see the full example, they do this exact. I took this out of the appendix, the appendix P2, but I'm going to give you the shortcut in it because it's a fairly easy shortcut to remember. And we'll use it again when we get to Friday's lecture as well. They'll bring this up. So what we've got here is we've got troubled savings and loans institutions are failing continuously, so that's an important thing, at a fractional rate of 5% per year. So 5% of the S&Ls are failing every year, continuously. So remember, hopefully, that there is a function for continuous change where we put the rate goes here times the time. Okay, and A naught is what we start with. So we're going to use this sort of formula. And again, you could say, well, we start with 1 or we start with 100. It doesn't matter what you start with, but what ends up happening is this gets modeled by a form. So our formula would be e to the minus 0.05, because that's 5%, right? And it's decreasing, so it's negative. If we were increasing by 5, it would be positive 0.05 times t. I'm going to use x because my t's don't look real good. Times a variable where x is number of years, number of months, if it, whatever it is, it's the time factor. And what we end up using, though, they show basically, they go through some calculus. What we will end up using for our function is, see if I remembered it right, 0.05 times this. Okay, and again, if you want to see where that 0.05, it comes basically because we would need to take, they go through that. This actually would give us the number, if you multiplied by that, what you started, it gives us the number of savings and loans remaining. So you subtract from what you start with, they get 1 minus that. And then what they do is they basically need to integrate. What do you need to integrate to get to that? So you could watch all the calculus steps, but here's the thing is you've got the percentage, sorry, the percentage right here that they give you up in the E, and you also have it in front of the E. If you remember that, that's really all you have. That will give you the function. And we only use this 1 or 2 times, so hey, you ever need to really use it in life, go look it up in the book and you'll get, that's what I would do. So this is what we're going to do. And so that's the way we set it up. See, do I have a question here? Now we go to the next one. So, then we can answer questions. What we would do is we would graph this as our function. Let's just see if it's a probability distribution. Okay, yeah, we'll keep, because we got to get to the important stuff, right? So let's clear this. We'll put in 0.05 times e to the negative 0.05x. And we're going to go from 0, because that x is time, right? So starting time is when we have all of them, and then they're going to, at some time in the future, yeah, we'll go to 20. I don't think we have to go too far out. See what our graph looks like. Yeah, it goes down pretty quick. Let's see if it's a probability distribution, and I hope it is, because that's what it's supposed to be. And if we go from 0 to 20, we might have to go further out. Yeah, it's 0.63. So 20 years, we still have some, because we're losing 5% a year, we still have some. So we might have to go out further, but this would let us know how far out we need to go. But it's looking like a probability distribution. Yes. Say that? Uh-huh. Oh. No, I just want to use it later. So I got it. So the thing is I have blacked it out. So it's not showing up. If this would show it up, I just say, I don't want to use it yet, but I don't want to also type it in, because it's kind of, that's what we're going to do next. Thank you. So there's these kind of distributions, which we spent maybe more time than we should have. Now we're going to get into this one that I've got there. So I'm going to undo this one. But anyway, when you get to the homework, it uses a different than 5%, but that's how you're going to do that one. Okay, let's get back. Okay. Formula for a normal density function is rather complicated looking. So that's what you're seeing there. What I've got in the graph is I'm using the standard, which is a mean. So remember, we were dealing with the mean and the standard deviation. We use the empirical rule for a normal distribution, but if you let the mean be equal to 0, there's a way to do that, standardizing it, and you let the standard deviation, or you make the standard deviation equal to 1, and there's a way to do that with every normal distribution. As long as it's normal, we can make it, we can standardize it, turn it into what they call z-scores. And so I've put in 1 here. So notice the mean is 0, so x minus 0 is still just x. So you'll see I just have x squared up here. The standard deviation is 1, because they standardize it. So 2 times 1 squared is still 2. And then there's just a 1 here. So what I'm using is 1 over the square root of 2 pi e to the minus x squared divided by 2. So that's what I have entered, and you're going to see it will actually give us the standard normal curve. So we can actually use it for all these calculations. There's also a way, there's a built-in feature in the calculator. So I'm going to show you both of those. Okay, I'll show you both. Mu is called the mean, and remember that's for the population. That little sigma is a standard deviation. So that takes us back to what we're doing. We won't have to calculate these. We will be given these. Okay, in this case. When we do this, and I'll show you that if you put that in, you get a graph like this. And does anyone remember if we went from 1 standard deviation below to 1 standard deviation above, how much area would we have under this curve? The empirical rule said about 68%. We'll see it's actually a little bit more, but 68 point something. But that's what so far we've done this with the empirical rule. Today we're going to do it with actual values. And we can do more than just one below to one above. Okay. And again, it gives you some information about the number E. So we've talked about that a little bit. It talks about those constants, and that the sigma, the standard deviation, we can make this equal to 1. So they have tables that are set up, so you could use the tables, but that's how I learned, because we didn't have the technology. Now that we have the technology, the tables, you have to, there's multiple ways to use them, okay? So if you want to learn that, there's example, I took all those slides out of mine. It's in the original, in the commercial version. So you can take a look through those, pull up a table and use them, or you can just use the shortened version where mu equals 0, the mean is 0, so we're going to see that, and that the standard deviation equals 1. Okay, so that's what we end up doing anyway. So this is called the normal random variable x. Okay, and it's what we use for most statistics. Okay, the bell-shaped curve. And again, as long as it's normally shaped, we could have various different means and standard deviations, but they can all be standardized by a calculation that changes it into this last one. And so what it allows us to do is to go back and forth between them. And again, the technology will take care of that for us. I'll show you in just a moment. Okay, so we're going to be using this one to do all of our calculations. Go forward. Okay, so that's what this is saying. We're going to standardize to make these happen. They do that with something called a z-score. And what that does, how that does is you take each x value, you subtract the mean from it, and you divide by the standard deviation. This will standardize and give us, all our values will be z, which will be a sort of a new variable, and it's a variable that has a mean of 0 and a standard deviation of 1. And again, you could, because if x is the mean, right, mean minus the mean is going to be 0. So z would be 0. If x is 1 standard deviation, you subtract the mean, you divide by the standard deviation, you've got 1. So this is how it gets standardized. So you could play with that a little bit. And again, we can always answer some of these questions that may not seem to be clear, but I want to just show you how we'll use the technology. Now, we might go a little bit into Friday with this, and that's okay. This is the way that you would use the table. So they want to find the probability that the z value is, so they're using the standard, between 0 and 2.4. On the graph, what that would look like is we're going from 0 to 2.4. They want the area under this curve, and we'll use the technology to do it. If you use a table, they have a large table, what you have to do is, and there's all these z values, you would find the z value of 2.4, and this is 0.00, so that gives us some extra decimal places, so it's not 2.41, it's 2.40, and it tells us that would be 0.4918, so 49%, 49.18% are in here. Okay, so that's one way. Watch how we do it with this technology. And I'll show you both ways. And then we're going to see that, because I wanted to get at least to this part. So I'm going to use this first one. I'm going to put enter. I'll go ahead and delete this second one, so because if we need it, we can get it again. So this is what you'd want to put into your calculator. On the graph, I'm going to go to the window. I'm going to go from -4 to +4. So that's four standard deviations both ways. That's usually enough to get everything. And I'm going to make my y maximum, my y minimum, I'm going to make 0 because it's not negative anywhere. And I'm going to make my y maximum 0.5 just so that I get a nice view, because it's all under 0.5. So I'm going to do the graph, and notice I've got a bell-shaped curve, and this is the standard distribution. because that's the formula. To find out what is the probability of being between 0 and 2.4, right? What I do, just like I did on that other one, I go to my calc, I'm going to do the integral, and I'm going to go from 0 to 2.41, or 2.40. What was it? It's 2.40, wasn't it? Yeah, I think so. Hope so. And we get that, and it shows me the picture, and it says it's 0.41 or 4918, which is exactly the table value gave me. That's all they did is in the table, they do all the calculations. Okay. So this is the kind of things you're going to be asked these kind of questions. What's the probability being between these two? Okay. You can use this graph. However, there's also another feature, and that's under this button called VARs. We've used that before, but it's the distribution. In the blue, it says distribution. So we're going to go second, distribution. This one you have to remember, the one we want to use is the normal CDF. Okay, normal CDF, we're going to put that in. But it's supposed to, let's clear. It's supposed to give me something. So second, distribution, normal CDF. There we go. This is what I want. This helps me fill in the blanks. So it wants the lower, which in this case was 0. And then I put in the upper, which it asked for 2.4. It was already a standard curve, so mean is 0 and standard deviation is 1. But if they're not, we can put those in here. We'll look at a couple examples, and then it pastes it in, and then I hit enter, and it gives me the value 0.4918. Same value, but notice I don't get to see the picture. So whichever way you want to use. We good with that? And again, the video shows you how to do all this. We're going to do it a few more times, and then we'll call it a day. We'll finish up with some of the later stuff, but this is the main thing. This will get you most of the way through the homework. So what about going from negative 1.37 to 2.43? Again, we're just pulling up our calculator. And if you look at the original slides, I'll show you how to do it all with looking it up in the table. But we could do this both ways. Let me show you using the graph. Now notice once you do one with the graph, the shading stays there. So what I found is I go back and I change this to like maybe negative 4.1 because it'll redraw it. Oops, 4.1. And now it will redraw it. And I can just enter these numbers, second calc. Negative 1.37 is the lower bound. The upper bound is 2.43. It gives me the picture. I see that's what it's giving me. It tells me down here going from negative 1.37 to 2.43 is 0.9071. 90%, 90.71% of the values are there. And it looks like that, doesn't it? Doesn't look like about 90%. It's a lot. So that's why I like using this one. With the table, you actually would have to do like 2 different calculations, and then you end up adding them together. So this is much smoother, and it gives you that picture. Again, we also could have done it with second distribution. Let me make sure I'm here. Okay, second distribution. And then I just put in my values, negative 1.37 and 2.43. And again, the nice thing is you'll see this one works well if they give you also the mean and the standard deviation, and they're not set up, they haven't been standardized yet. You can actually enter them here, and it will do the same. It will take care of all the details for you, but it gives you, after you hit enter, the same number. So, but I would use this after you feel comfortable. Maybe try that standard normal distribution, the integration. You see the picture, you see the answer. Okay, that makes sense. This one will work as well. It'll give you that direct value. But a lot of the homework, that's all they're asking for. What's the percentage under the curve? There's a number of problems. There's a couple at the end that are word problems. We'll start on Friday with those and then easily jump into the last P3 part, which will go a lot quicker because it's just really looking at formulas and bringing them in. Okay, but get some practice with this, the technology. If you've got a Casio, there's a video in there that will show how to use the Casio. And I had, like I said, I had to update my operating system, so I'd be happy to help you with that. It takes a little bit of time, but we can get your. In fact, I even have the download. I don't think I have my cable, but I'll bring my cable on Friday. If anyone has a Casio and needs to get theirs updated, we can do that like during office hours or something. Questions? Is it sort of making sense? Okay, give it a try. It's all in there, and we're almost done. Only 4 more slides.